Hello, everyone. Welcome to join the live streaming of Photonic Research. We set this program to introduce exciting research published in Photonic Research. And tonight, we organize this event a little bit different from what we did last time. So I will spend around 10 minutes to introduce Photonic Research, which will be followed by the introduction of the work by the author. Then we'll reserve 30 minutes for in the panel discussion. We will ask the question to our guest. And there are 4 guests for tonight's panel discussion, others for the work, and one is a guest who is an expert in fintech. That will be a very exciting conversation. Actually, before this event, I just have a couple minutes discussion with our guests. You will be surprised by the knowledge that will be delivered by our guest. So let's share my screen and make a brief introduction of the journal. So welcome to join us tonight. Photonic Research. You probably have heard of this journal. It's a new journal compared to many other conventional journal in the field of photonics and optics. It was launched 10 years ago. From day one, it was launched. It was positioned as a journal that will showcase the research that is not just correct, but also introduce new and important results in the field. And the journal is doing pretty good work. In the past 10 years, it has gradually attracted a lot of attention from the community. So for last year, the impact factor is 7.6. I will say impact factor cannot just represent the journal itself. There are many things to evaluate whether the journal is a great platform. But impact is just a reference number to tell you how we... Is just a reference number to tell us the situation status of the journal. And for the time being, looking back for the past 10 years, the impact factor has been monotonically increased all the way. And in addition to myself, the journal is backed by a very strong editorial board. So we have two experts who have great reputation in the field of photonics. For example, Yuri is a well-known expert in metamaterials and is a very theoretician who covers a broad spectrum of topic in the field of optics. And Yao is an expert in quantum photonics. They have been working with me to oversee the growth of the development and of the journal. And for the past 10 years, for example, as I said, the journal has been increasing. So we want to compare the position of the journal with our peers. So this is a list of the top 15 journals in the field of optics and photonics. And as you can see here, photonics research is doing pretty good work. And it's worth noting, actually, if in addition to impact factor, you might want to pay attention to the number of papers that's published in the journal. I would say photonic research is growing in a healthy way. In a sense, we didn't control the number of papers. Instead, you can see annually we publish around 300 papers. And it can still maintain good reference impact factor in the field. And this is just some papers we selected to showcase that for the paper published in Photonic Research can attract sufficient attention from the community and also from the subject covered by the papers. You can see the subject covered by Photonic Research really cross a broad topic in the field of photonics. For example, from the conventional topic on silicon integrated photonics and imaging, instrumentation, we also cover topic about this emerging topics such as deep learning in photonics. And every month, we do have a different way to promote papers published in Photonic Research. So for example, each month we select one paper to be on the cover page. And in addition to the paper selected for cover page, 10% of paper will be selected as editor's pick. And in addition to that, each issue, we have one spotlight papers. And for the paper selected for Spotlight, Optical Publishing Group has a committee to write a news article about the papers. And since last year, we also have another way to promote papers published in photon research, that is press release. So now we have one quote every month, or every month. So those papers should be the candidate for a Spotlight. And then in the candidates, we also choose one paper for press release. For press release article, an Optical Publishing Group also have committees to work with authors to write a longer news article to promote the work. In addition to those, as a partner journal that is co-published by Optical and the Chinese Laser Press, photon research surely has some advantages. For example, there are two platforms to promote papers published in photon research in Chinese or English. And we find all kinds of ways, for example, like newsletters to promote those papers published in the journal. So in addition to, this online media, our editors has been really proactive, spread words about the journal. Those are just snapshots of photos showing the papers publishing that the journal was promoting various venues, different conferences, workshops. And in addition to that, we also leverage on the platform created by Chinese Laser Press. This you can see different WeChat account created by Chinese Laser Press. They truly got a lot of attention from the community. And I can say probably this CLP's WeChat platform is one of the most popular platform online. You can see that about 200,000 fans subscribed for this platform. And almost daily, I read articles from this platform. And specifically, this slide shows how we leverage on this WeChat platform. For example, when there's new subject or new papers published every month, sometimes we have news article on those papers. And in addition to these papers published in the journals, we organize workshop on feature issues every year. And also we have this special webinar interview that is used to interview this pioneering research in the field of photonics. And for all those activities organized by Photon Research, we have this news article promoted by the WeChat. And you can see really the reading, the number of views are really impressive. And in addition to that, we also, starting from last year, we also create a new form to promote young researchers. We understand, in addition to senior research in the field, our graduate students and our young faculty members, they are the future for the field. So we do want to do something to help them out. And one thing we created is to add assistant editor. So in addition to associate editor that helped review articles, we also have assistant editors. They work together with associate editors to oversee papers submitted to the journal. And in addition to that, for the news article we created to promote papers, we also invite our assistant editor to write a summary about the work. So while we're promoting the work, we also promote our own assistant editors. And in addition to that, I also want to mention the Editor-in-Chief Choice Award. Every year, we have two papers selected for this award. I can tell you there is no specific, preference to any topic. The only criteria is innovation, significance, and innovation. So the award can be given to a small group, or a large group, or theoretician, or experimental group, as long as the work can fall in the category meet the criteria, as I said, significance and impact. And for each award, the awardee will get 10,000 Chinese yuan, or the value of the money doesn't indicate the value of the work, but it really a token for us authors. So this is a slide telling you about this interview webinar I just mentioned. It was launched in 2021. Our first guest of honor is Professor Martin Scully, who is in quantum photonics. It was well received. And last year, we interviewed Professor John Bauer, and this time we changed the interview in a different format. It became a conversation between Professor John Bauer and his former student, Professor Lin Chang, now is professor at Peking University. And this year, the conversation is between Professor Connie Chang and his former student, Professor Hao Sun in Tsinghua University. I would like to encourage you to send a name to us if you think there are your mentor, professor, is a pioneer researcher in certain field. We'd love to solicit name from the community to prepare for the next interview. And in addition to those, to promote the journal, every year we have one workshop dedicated to one interesting subject. Sometimes it was subject of the feature issue, but it was not limited to this topic. It could be any topic that is of interest to the community. For example, we have a cover topic on optical microcavities, silicon photonics, and in 2021 is about deep learning photonics, and 2022 is about innovative photonics. And last year, the subject is about optical metal surfaces. And in addition to that, last year, we have some interesting activities to celebrate the 10 years of photonic research. I would like to thank Tsinghua University to host the first workshop to celebrate the 10-year anniversary of the journal. And also after that, we organized the second one in USTC and the third one in Zhongshan Daxue. And those are the feature issues we mentioned. So every year we come up with subject that is suitable for feature issue, and those are subjects we have organized. And again, we would love to solicit a subject from the community. If there is some interesting topic that you think that is suitable for a feature issue, please send an email and contact us. And here, email address. We would love to hear more from you. Okay, I think time is up. I wanted to save more time for our guests. So tonight, you hear a very exciting topic. It is about efficient option pricing by using the integrated photonic circuits. And we would love to hear more from the authors. The talk will be from Professor Hui and Dr. Hui Zhang. So Dr. Hui Zhang, the stage is yours.
Okay.
Yeah, there you go.
All of you can see the slides, right?
Yes.
Okay. I will introduce our work, this time published in the Photonics research about the photonic computing chips for the finance applications. So for the background of the photonic computing, which is actually not a very new story, that is the global computing power is always increasing and new hardwares are required. And the popular research topics nowadays for the more techniques includes the photonic computing, quantum computing, memory-state computing, and chiplet technologies. And among them, the photonic computing has some certain advantages, like the low latency, high bandwidth, and significantly improved energy efficiency. The photonic computing, from the physics realizations of it, we can divide it into the photonic classical computing and the photonic quantum computing. So photonic classical computing make use of the wave properties of the light to realize some computing functionalities. Most of the works are focused on the realization of the photonic neural network in recent years. There are many different devices that are utilized to realize the photonic neural network, like the microring, diffractive plane frequency comb, Hazenda interferometer, and so on. The photonic quantum computing, especially it make use of the particle properties of the light, and the photonic quantum computing is also one of the mainstream hardware platforms for the quantum computing. From this picture, we can see that the hardwares for realizing the MZI-based neural network, photonic neural network, and the photonic quantum computing have some features in common. They are based on the interference properties of the Mach-Zehnder interferometers. That lies the foundation of our research. That is, make use of the Mach-Zehnder interferometers to form different structures of the networks. So to realize the multiply accumulation operations in the artificial neural network, or it can also be used to realize the qubit manipulation. As we know that all the quantum circuits can be decomposed into the single qubit and two qubit. Then both the single qubit gates and two qubit gates can be realized by the Mach-Zehnder interferometers. So that the MZI-based network also used for the quantum photonic circuits. Notably, the two qubit gate here, it has a certain success probability. So this results in some hurdles to realize a universal quantum computing. But this platform at that stage can also be used for demonstrating some interesting algorithms. There's some milestone works, review of some milestone works in this field, like the demonstration of the control NOT gate, the demonstration of the boson sampling, and the MZI-based optical neural network. Our group also have some preliminary results in this field, including the complex valued neural network, the on-chip training method of the photonic neural networks, like the gradient-free method, gradient-based method. And more recently, based on these capabilities, we developed the quantum autoencoder network on chip and the finance computing on the photonic chip that will be introduced. So the finance, in brief, it deals with the uncertainty in the future behavior of an asset, also the prices and the returns it may have in the future. It has some challenges, like its challenges comes from its complex system and the history strongly correlated data. So, cause it's very difficult to predict. The finance computing requires many computations, so it cannot. Nowadays, it cannot be dealt with the manpowers. It will require a lot, large amounts of electrical powers and programming and coding. So, some quantum theories also being proposed to accelerate the computing of the finance problems. According to their the problems they solve, the finance problems can be divided into the three main categories. The first category is the portfolio optimization problem, which decides what kind of assets should be included in an optimum portfolio. And the second is about the invest strategies, like how to detect opportunities in different assets in the market. And the third category is the estimation of the risk and profit of a portfolio. Different approaches corresponding to these problems, including the combinatorial optimization and the machine learning to the invest strategies problem, and the Monte Carlo methods to the profits estimation. So correspondingly, different quantum methods are also proposed, like the quantum optimization, quantum machine learning, and quantum amplitude estimation. We are going to focus on the prediction of financial derivatives using the quantum amplitude estimation method. So for the option, it has two features, the strike price K and the spot price at the maturity ST. So if the ST larger than the strike price K, we can make some profit. And the calculation of the payoff is in fact to calculate the mean of the estimation, the expectation value of the probability distribution of this evolution of the stock prices over time. There are two classical approaches for it. One is the BSM model, which is based on solving the stochastic differential equation. But this approach oversimplifies the market dynamics, so its performance in the real applications are not that good. The most commonly used method is the Monte Carlo simulation method. It needs to sample numerous paths of asset dynamics, so it is very slow for the prediction. The quantum amplitude estimation algorithm was proposed to accelerate the estimation of the mean of the probability distribution. According to these brief derivations, it can achieve a quadratic speedup. The quantum amplitude estimation can achieve a quadratic speedup comparing to the Monte Carlo method. The algorithm itself in the binary approach, in the binary implementation, can be tested on the IBM Qiskit. And here we show the circuits of the operator A and operator Q. We can see that the circuit is very deep, so it requires a lot of control NOT gates and require high gate fidelities. This caused some hurdles in the NISQ area, where accessible quantum qubits are only 5 to the maximum accessible quantum qubit are only 50 to 100 qubits. For the photonic chip, although it has high fidelity single mode rotation gate, the lack of deterministic control gates also make it very difficult to implement this algorithm. So we do these two things to transform the quantum model to a linear optical circuit that can be implemented on the photonic chip. The first thing we do is to optimize the binary algorithm to a unary algorithm. And then we transform the control NOT gate to the linear transformations. So by this way, we transform the quantum model into a linear optical operator model. And by designing the linear optical operator by beam splitters and phase shifters, we come up with this photonic circuit model. The unary encoding of the stock prices is shown like this. Certain passes of the stock prices we divided all the passes of the prices, evolution of the prices into several bins. The passes belonging to the same bin are corresponding to a single base of the unary representation, and its coefficient is equals to the number of the pass versus the entire numbers of the passes. So by this way, we can calculate the expectation values of these probability distributions and to get the payoff. Then we transform the control gate to linear transformation. This circuit, it involves two states. One is the unary base, which we can understand it as a high-dimensional encoded qubit. And another is a binary encoded ancilla qubit. So to keep the Hilbert space to be the same, we add an ancilla waveguide, which is an ancilla path mode to each of the unary base. So for the final circuit, we have two waveguide passes for each unary base. This method, it makes use of the scalable path modes on chip to overcome the difficulties of implementing control gates in a quantum model. Then we design the algorithm, which contains three functionalities: the price distribution, the payoff calculation, and the amplitude estimation. The three modules. This is the algorithm model of the option pricing. Now it's still shown in the high-dimensional qubit and the ancillar qubit. Then we transform it to a linear optical operator model. So in this model, we have three main operators: the swap, the rotation Y, and the XDX operator. According to their mathematical expressions, we design them as the structures, the devices on the photonic circuit, and replace them in this previous model, so we get this final photonic circuit model. Then we perform the experiment on it, and here we shows the results. This picture shows the calculated payoff represented in the angles. And we observe a close matching between the theoretical value and the experimental value. This picture shows the error convergence of the payoff estimation. This convergence, it shows in this picture, it shows near quadratic speedup to this Monte Carlo simulation curve. This is about how we implement how we upload the market data onto our photonic chip. In this part, we involve the using of generative adversarial network. So it is used to upload the market probability distributions with more close to the market trend. For example, if we already have a GAN model that is trend and new data is coming, this trend GAN can be used as the initial probability distributions. So it will accelerate the convergence, the estimation convergence. This implementation is in a hybrid mode. The generator of the GAN is implemented on our chip and trained on the chip. Then the discriminator is implemented off the chip and trained off chip. The training aims to make the discriminator cannot tell that whether the incoming data is from our generator or from a real market data. So at that time, the generator can best mimic the probability distributions of the market data. We test this model on two distributions, the binomial distribution and the normal distribution. Both shows a good convergence in the uploading process, which converges to a final L2 norm of about minus 18 dB. This unary approach also has some advantages over the binary approach in its algorithm architectures. Actually, the unary approach will show more clear and simpler chip architectures compared to the binary approach, so resulting in less CNOT gates, partial swap gates, and their combinations in use by the entire circuit. And as we can notice from the simulations from this paper, for less than 100 qubits, the unary approach can always show an advantage over the binary approach. Here goes our summary. We implemented a option pricing model on the small scale quantum photonic computing chip with some quadratic speedups demonstrated. We also implemented a generative adversarial network. the quantum finance applications shows a trend of the three separative directions. The quantum optimization for the portfolio optimizations, and the quantum machine learning for some invest strategies, and the quantum amplitude estimation algorithm for the risk and profit profiling. Thank you for the listening. That's all for my presentation.
Dr. Zhang, thanks a lot for making a nice introduction of your work. So I do think there are so many things that are behind the slides, right? People will need to dive into your papers to know more about your work. But other than the research itself, I think we'd love to hear your personal opinion about the work. So let's start a panel discussion. And actually, I want to start with our guest, who is not author on this paper. So it's a great honor to have Professor Paul Griffin from Singapore Management University to join us tonight. He is an expert, world-renowned expert in fintech, and he has been advising companies since 2014. So it has been 10 years. He has been really active to oversee various technologies applied to financial industry. And he has been moderating panel discussion fintech many times. So it's perfect for having him on board with us. So Professor Griffin, my first question for you is, what specific financial problems can quantum computers solve more efficiently than classical computers?
Okay, so I think always think of this in very general terms. Quantum is a probabilistic mechanism, so I always think that the best way to generally think about what sort of problems are the probabilistic, sort of non-deterministic problems. I always say that if you want to do accounting where you have to balance books, you get invoices, you have to pay them, things have to match, 1 + 1 has to equal 2 every time, then that's not the case to use quantum computers. I mean, maybe there is something there, but I think generally that type of precision is best done by classical computers. But in finance, the probabilistic non-deterministic problems are very many, whether it's talking about risk, credit risk, market risk, there's many types of risks. That's all probabilistic. Risk is obviously inherently unknown. Then we have the investing side. So as was mentioned in the great presentation about option pricing, you're looking at the price of an option in the future. Nobody knows what that actually is going to be. So again, that's a good probabilistic. Optimization, so that's another area. We're constantly optimizing portfolios. Maybe you optimize your own personal portfolio. Companies need to do it. Governments need to do it. We're optimizing sort of types of assets. So they're very complex, a very large number of assets. So optimization is another area. Also coming and working with SGX, Singapore Exchange, on optimizing settlements, transaction settlements. So even in the back office, even in the middle office, there's still lots of sort of probabilistic problems that I think quantum computing is very kind of well positioned to solve. Again, I guess at a general level, then NP hard type of problems are the area which is worth looking at if you want to start to sort of look into which type of problems are best to look at.
Yes, that's interesting. You mentioned this non-deterministic feature of a problem in financial industry. So how do quantum models account for the uncertainty and the volatility in financial markets?
Okay, so if you look at so first of all, the uncertainty. So the easiest thing to do is to think about mapping the uncertainty in price into a superposition. So that's the first thing to do. Then volatility, really, you're looking at, say the example of portfolio optimization. What you need to do is create a diverse portfolio where maybe one stock price goes up at the same time the stock goes down. So you can reduce your risk by diversification. So for that, you will use entanglement. So the models use fundamentally sort of superposition entanglement to create a model of the market between the various assets.
Oh, that's great. Thanks a lot for providing your perspective from users' perspective on this work. So let's move on to the next guest. So Professor Liu is senior author on this work. So I'd like to hear his opinion. Professor Liu is a chair professor of quantum engineering and science at the Hong Kong Polytechnic University. And I also noticed he has affiliation with Nanyang Technological University. So Professor Liu, in your opinion, could you explain what a photonic integrated circuit is? Because there might be some audience who have no background about this technology, and they would love to know more about it. And can you also tell us what components are typically integrated into a photonics quantum circuit, and how do they work together to perform the quantum computation? Oh, Dr. Liu, can you unmute yourself?
Okay, thank you, Professor Yang. And I think this is a good opportunity and for us to meet all of you with you and all the audience and enjoying this learning and together for this photonic circuit and quantum finance. Photonic circuit, actually the first and the big impact of the product is for this fiber communication, the 100, 400, 800 transistor. I think this is a major driving and the big impact from the photonic circuit technology. But behind all this one, photonic and circuit technology also have a lot of other application and integration and laser source with a photo detector, either for next step or the single photon detector. So the photonic integration circuit is a platform. It's based on the CMOS semiconductor fabrication process. It's the next generation and the semiconductor technology extension to photonic technology. This is and history and market requirement. Then the research is always around for this area. And photonic optical computing actually is not a new topic. This is a very, very old topic. This topic can be similar for IBM start the digital computer before the analog computer. Actually, optical computer also there. But the problem is optical computing technology cannot compete with the chip, cannot compete the microprocessor and the last and 15 years. So and during this period, and IBM and all of the microprocessor technology built up, the laptop, data center, and mainframe computer. Then the big trouble for this optical computing is what is the platform? What is the engineering integration platform for instrument? Can they make the optical computing all the component in the single chip? But the silicon photonic provides this good opportunity for optical computing 10 years ago. So the people more and more and pay more attention after today. And the computing technology is a big requirement for the market. Because of IA technology, artificial intelligence, they have the strong simulation, machine learning, all of requirement. And actually, a lot of the finance model is very difficult for the computer science. Also still there. For example, a lot of the equation computation job from the bank using mainframe also is a very struggle. This is another problem. So you can see this is a good mesh. And the silicon photonic provide a good integration for the traditional optical component and to the single chip. Integration and to the single chip. Then the optical computing also is become a new question bring up for the bank and the traditional and modeling and simulation model. So this is the question from two sides. and focus on this project. So the traditional silicon photonic technology, and now we are working on the linear optical model. And I think the paper is a big contribution. She created a different model and the coding of this quantum algorithm to linear system until operation by the chip. Get the simulation result, validation of the result. They're looking for the model to model the transfer method. Solve this one on the operation price problem and coding by this algorithm. So this is a contribution for this work. I think in the future they have more work and more of this part from the linear to non-linear optical coding and looking for more difficult of algorithm to get a solution. This is my answer for Professor Yang.
So you mentioned this integrated photonic circuit, integrated photonic is future technology. So the next question will be, how scalable are current photonic integrated circuits for quantum computing, and what are the anticipated future development in this technology to enhance the scalability and its performance?
I think the optical computing properly and have some solution for this and my friend and the clock computing may be part of for the digital computer and the chip maybe. And I think some big company also try to looking for and either of microprocessor, optical computing chip integration, looking for this and the two things and become the civil and the computation time and the computing labor. And this is one of industry interesting technology now the approach. But this is difficult because this is really is high level integration either of this mathematical and integration technology. I think this is a challenge. But this is possible, and this is 100% and the computer science and the technology and working with and the silicon photonic integration circuit. I think that's a really cutting edge technology. The few group of people working together and become the next generation hybrid micro digital optical microprocessor chip with and optical chip computation chip integration and technology in future. I think this is probably next 5 years you can see some good result coming and delivered by industry. But for the optical computing properly is and have the long way to go and 5 years or 10 years. And I think the big trouble is even if so far we demonstration lot large scale of cubic and quantum computer technology, either of use a superconductor, either of ion track, and these are two major of approach by industry. But the challenge is the accuracy. The accuracy and is a big trouble for superconductor technology. So far, you can see and based on the quantum finance and how many people can demonstration use a 10 cubic or 20 cubic can do the case study, but the result is very few because the accuracy and the computation fidelity is a big trouble for this quantum finance. Silicon photonic is replace of this things. You know that we do the 16 cubic of this silicon photonic and fidelity and some and the molecule spectrum can be meet 90%. So this is a very exciting result and going to publish soon. And we also use silicon nitride and do this and computation that can around the chip 3 cycle, and also the photon can survive. This also is a very surprise. There's a silicon nitride, and either of a nonlinear material that provide the low loss for this integration. The second thing, so you can see that all of the computer use the silicon, and the quantum computer should be basic on the it's a computer. The computer should be integration with the mainframe, working with the mainframe. So there's no other too many choice. I think the semiconductor is a big driver for this commercial and high-tech and manufacturer. This nobody can bother this one. Semiconductor too powerful. So the silicon photonic is a good position and a good role, and for the future quantum microprocessor. This is I trust.
Thanks a lot, Professor Liu, for sharing your insight with us. So I'll move on to the next expert, Professor Quick. Professor Quick is a faculty member in National University of Singapore, and he has long history in the field of quantum physics. So the first question for you is about your motivation to use photonic integrated circuits for quantum computing. What are the advantages?
Right. Can you hear me?
Yes.
Thank you. I think one of the main advantages of quantum photonic chips for quantum computing is simply because it works at room temperature. Now, if you compare with the current implementation of superconducting qubit, which works at very low temperature, ion traps also works at low temperature, and more recently, the neutral atoms quantum computer, which also works at low temperature, then there is a clear advantage in terms of precision control as well as in terms of working at room temperature. Unfortunately, of course, photons do not interact, and so it's hard to get them entangled in that sense, unless, of course, we have incorporate nonlinearities. And that is actually a current one of the main challenge of photonic quantum computing. But nevertheless, there's been a lot of research done to try to look for suitable, and I think Professor Liu just mentioned earlier on, silicon nitrate, to look for suitable nonlinear elements that can push the frontier forward. Now, there is also another important and often neglected aspect of photonic quantum computing. That is the fact that it dissipates very low heat. You know, light do not interact with matter, and at the same time, they do not dissipate heat as much as electrons. And so this is currently, in fact, one of the main motivations behind what's called eco-friendly devices. So this is an important aspect of integrated photonic chips. If we predict that the whole computing industry is going to consume 30% of the world global electrical consumption in the next 50 years, then integrated photonic chips would make a very good candidate for reducing that energy cost.
That's great. I think it will be helpful, actually. Maybe you can educate us about to explain how photonic integrated circuits can be used to create and manipulate the qubits in quantum computation.
Right. In terms of qubit, photonic qubits exist in various kinds. Now, when quantum computing was introduced way back like 20 to 30 years ago, linear optics was supposed to provide a good candidate for quantum computer. And at that time, in bulk optics, one make use of horizontal and vertical polarization, essentially the 2 degrees of freedom that a photon can possess as zeros and ones. Now, this has changed over the years. In integrated photonic chips, unfortunately, polarization degree of freedom is not a preferred mode of encoding. One of the reasons being that a beam splitter for a horizontal polarized photon is not quite the same as the beam splitter for a vertical polarized photon. And so there are other ways of doing encoding. And currently, of course, there are some preferred mode, time beam encoding, for example, and also in many cases, dual real. But whichever encoding you use, it stems from the fact that you can manipulate the internal states of a photon to form a logical bit. And not just a logical bit, it's a logical quantum bit. And this is how the arena got vastly developed. But another important aspect, which is often a challenge for linear optics, is entanglement. It turns out that because photons hardly interact, entangling gates become very expensive. But in recent years, there's been some work done to show that perhaps we can exploit what is so-called graph states. So these are states that are highly entangled. You prepare them well in advance, and then on photonic chips, and then by doing a series of single qubit measurements, you can actually realize entangling gates. And so this method of doing has been actively pursued in many research by many research groups. The interesting thing about graph states encoding, including crazy graph states, whatever they call, is that you have fault-tolerant property. In other words, if you look at superconducting qubits at the moment, you can realize qubit over a single, a single qubit gate. But the single qubit gate's fidelity is pretty low, or sometimes not sufficient when you concatenate them together. So the idea is that if you now have fault-tolerant computing on photonic qubits, then you actually solve a very important aspect of a quantum computer. That is that you now have a qubit that is, well, it's not just a single qubit, but it's made up of many physical qubits. But nevertheless, it can address the issue of error correction. Of course, in the last few weeks, there's been some progress in neutral atoms. Neutral atoms have been shown to be able to do fault-tolerant quantum computing by Michel Lukin's group. But the disadvantage of a neutral atom, as usual, is its low temperature. Does that answer?
Thanks a lot. Yeah. So I do want to ask you one last question, because there is one feature that's critical for computation, that is accuracy. So what do you think how the photonic integrated circuits can contribute to the implementation of quantum algorithms, especially in the area like quantum error correction?
So there are a few aspects to this question. The first thing to realize is that photonic quantum computers are just as good, if not better, in some cases, than superconducting qubits or ion trap. Gate fidelities may just be comparable, but nevertheless, what is perhaps more important is that there exists an algorithm, specifically for photonic platform, that cannot be matched actually by superconducting qubits nor by ion trap. And this is the algorithm of what's called boson sampling. And so boson sampling is specifically a very simple algorithm. In some sense, is like looking at the probabilities of where the electrons go. In this case, where the photons go after they have passed through the device. Now, so if you have three or two photons going into a device, and you want to know the output of two photons coming out from the other end of the device, you would like to say, okay, let's compute that probability. And that probability of two outputs in, two photons in and two photons out appearing on the other end, and you require that the two photons are at completely different output ports. Actually, is that probability is related to a mathematical problem called permanence, or in some cases we call it Hafnian. And it turns out that while permanence is very easy, permanence is actually a classical concept in some sense, is related in some sense to determinants of a matrix, if you know mathematically what determinant of a matrix is, but it's related somewhat, except that for determinants, you have pluses and minuses attached to all the entries, all the products of the entries. Permanence is just simply all pluses. Now, it turns out that the mere changing the minuses to the pluses actually makes the problem even more complicating. At least classically, we know that is numerically very difficult to compute permanence. And because it's numerically difficult to compute permanence on a classical computer, we now have a sharp P. Actually, it's a sharp P hard problem, which cannot be done on a classical computer if we can do it large enough. So, and it is also very tolerant when it comes to photon loss. You'll find that it can resist photon loss, and therefore, even if on a large chip, if you can compute permanence, you'll find that you actually have a quantum advantage in that sense over a classical computer. And this aspect is perhaps very important because it means that not only does photonic qubits offer a new way of doing computing, it has a clear example of a classical algorithm that is completely difficult on the classical computer, but is very easy on a quantum computer. Well, on a photonic quantum computer. So perhaps this is something we should harness, and there has been some effort, including Professor Liu's group, in trying to push this frontier forward. And it turns out that computing the boson sampling and computing the permanence of boson sampling and also the Hafnian can be very useful for certain applications like perfect state graph matching and also quantum chemistry. And that's been actively being pursued at the moment.
Thanks a lot. So, Dr. Zhang, you're the speaker of the talk tonight. I just reserved two questions for you. The first one is about the unary approach you used in this work, right? Is there any potential to apply this approach to optical quantum chip in other fields other than fintech?
The unary approach we used in this paper, we can understand as the high-dimensional encoding of the quantum qubit. And so with this understanding, actually it has some applications in the has some usage in the quantum information processing to convert some algorithms from the binary version to the unary version. Also, it can also have some applications in the photonic classical computing. Since some quantum algorithms, they can have some special advantages that can be translated to the photonic classical computing language. So by using these methods to convert binary encoding to unary encoding, these certain algorithms can be employed to realize some advantages in the photonic classical computing.
Okay, as an expert in the field, other than the approach you used in this work, in your view, what are the other techniques that can be utilized by optical quantum chips to ensure and improve the stability, fidelity, and reliability of computation?
I think this can be divided. This question be divided into from the science or the algorithm perspective, and from the engineering perspective. So from the science and the algorithm perspective, that is to see if there's any encoding ways to bring some advantages to the implementation. Unary encoding is one way, but it will not be applicable to all of the algorithms. It depends on what the specific algorithm is, and to see whether the unary in this specific algorithm can achieve some advantages. There's also some denoising mechanisms that can be used for some noise on the photonic classical computing occurred during the computing process. We can employ some denoising algorithms, like the autoencoder we have investigated to on the chip to denoise the computation results. And from the engineer perspective, there's quite a lot of ways to do that, because for example, the chip we have used mostly is based on the thermal optical modulators. So we to balance the heat, to help the heat dissipation, is one of the way we keep the chip stable. And this can also be achieved from some active crosstalk elimination algorithms, techniques. That are some algorithms to do this.
Thanks a lot. So, one last question for you. So in your work, you have one dedicated optic chip to solve one problem, that is option pricing, right? But in reality, normally you need to deal with a broad range of financial tasks at the same time. So in your view, in the future, what is more preferred system? Should we develop the quantum chip leaning towards a multiple dedicated function system integration, or one multifunctional system? So which is more realistic?
I think I think both way is very promising in the future, to have some dedicated functionalities for certain tasks and then integrate them together, like what we do now in reality. We are actually doing this. And another way is to make a universal chip that can accommodate all of the computation tasks. This one may more like this question, more like to develop a new electronic computer, new device like the electronic computer that can do any kind of computations. So this is much more difficult, and it's promising, but much more difficult in needs a lot of efforts for it, for doing this. The photonic computer, I think most of the researchers would like to would like the photonic computing to for some dedicated tasks rather than a universal computer, because the photonic performs the computing in an analog way, which has some concerns in the accuracy. It is more preferable for the tasks that doesn't care too much about the accuracy, but has larger thresholds for the error tolerance. But for the quantum computer, the true effort is it has to be develop a true quantum computer that can replicate, that can replace the classical computer that's doing the universal operations for that.
Thanks a lot. We're a little bit over time, but I do wanted to ask you one more question. I think it will be interest to audience. This is a cross-discipline research, and we want to hear things behind the story. Professor Liu, maybe you can represent the team to answer the question. I wonder how you form the team, because this is a really uncommon topic in the field of integrated photonics. And how to come up with this topic and form the team and push things forward to get this beautiful paper.
Actually, this is a very good question. I'm not the key person from the team. The key person is Professor Quick. He needed initial of this and the collaboration to me, and he is working on the quantum physics more than 30 years. He's a PhD, also working on the NUS CQT and the STAR CQT. He's the one, the pioneer guy, and the quantum and technology in this NUS CQT. We're lucky, and Singapore invested the quantum physics 30 years ago. We have the very strong quantum physics base. So the Quick is one of the representatives of this group of the people, and he is very smart. We have very interesting story. I think the 7 and 8 years ago, the CQT conducted one the quantum special needs technology the conference. I just go into the take a look and learn some things, meet him. We are his good friend a long time ago, but meet him in the conference. Then he talked to me, actually you are interested of this quantum technology? I said, no, yes or no, and maybe I can learn some things. Then during the lunchtime, he bring and 4 of us go into the AUS staff club, and he went to one lunch. Actually, during the lunch, I think I also have one guy. I think maybe Quick, I also can remember that Chao Yang also in this lunch, right? And the 4 of us, we just chat of this quantum technology and this one, but he didn't initial offer this collaboration. Then after lunch, then he talked to me and say, hey, you know that I want to use a photonic chip to build up the quantum technology. Can you help me? So after this one, I think no problem. We are looking for new approach. We are also working the cutting edge of this one. So from the Quick, we are partner working on, in the initial, the early stage, working on silicon-based quantum technology. Then after this one, we are bring a lot of people join this group. For example, the quantum finance, Jose and Paul, and also have another gentleman, Miller. We also working together and see what is we can do between the silicon photonic chip and the quantum technology or the quantum finance of different parts. So we have very good tradition of this working on the research of the cutting edge, multidisciplinary. This is become our part of the research life. So, and we have a lot of different partners, and we working together, we respect each other. We also will be careful maintenance of this research environment in the Singapore, even if we are in a different place, but we always can easily to working together, we talking together with, we are share the result, we are happy each other. So this is wonderful. So you can see the today the meeting, somebody in the China, Shanghai, somebody in the Hong Kong, somebody in the Singapore, and you are from United States. But it's nothing for us, communication working together.
Thanks, Dr. Liu. I think it's wonderful that you share your experience with us, and also so that you truly give us some take-home message. That is to make a beautiful work and come up with exciting idea. And we should attend a conference. And in a conference, don't be silent. Be brave and be proactive, reaching out to people and to talk about the things you never thought of before. Don't be afraid of being turned down. The person you talk to might be reluctant. But just as Professor Liu said, if there's an exciting idea, people will be moved by you. And then, well, here we go. You will come up with a team to support your career, to work on some really exciting things. And so for now, it's time is up for tonight's event. First, I wanted to give my special thanks to our guests tonight. Thank you all for sharing insight with us. I also wanted to thank all of you who attend this event because of your support and participation so that our event was successful. I really look forward to meeting you again next month. I will introduce another story to you that is about work published in photonic research. And I truly hope everyone have a wonderful day, and I will see you later. Bye.
Thank you, Professor Yang.
Bye.
Thank you,
Thank you,
Professor
all
Yang.
the audience.
Thank you.
Thanks a lot.
Okay, thank you.
Thank you.
Okay, take care.
Thanks a
Bye-bye.
lot. It's my
Bye-bye.
honor to have you. Bye.
Bye bye.
Bye.